Hi, my name is Ayush Agarwal, and today I'm going to be presenting a paper on American Sign Language translation using deep learning. Today, in North America, there are approximately 500,000 people who use sign language as their primary source of communication. However, people using sign language find it extremely difficult to communicate with others who are not familiar with the language, and this limitation can create substantial obstacles in matters such as hospital visits. Currently, interpreters are required to enable communication with others, but this can be expensive and may not be easily available. Therefore, the purpose of this study is to build a machine learning model using deep learning that can translate American Sign Language with no manual intervention. So, a bit of background research. American Sign Language is a language composed of hand and facial gestures and has many attributes similar to English. It has a different grammatical structure, however, but also has its own dialects and accents. Existing research in the field of sign language translation involves using sensors such as motion, electromyography, and kinetic sensors, while research using computer vision relies on using only cameras to take videos of people signing. Most studies, however, build models to classify only numbers, alphabets, or words, and very few attempts have been made to construct actual full sentences. Now coming to machine learning. Although there are various types of algorithms and concepts in machine learning, I'll be focusing on artificial neural networks which try to mimic how a human brain works. Neural networks consist of nodes which act as neurons, organized into layers with an input, hidden, and output layer. The weights between the layers, denoted by the arrow in the diagram on the right, are used to estimate outputs given certain inputs, and the objective of the model is to determine the weights which will minimize the error. Deep learning is essentially just using multiple hidden layers in order to enable a neural network to learn complex features. A CNN, or a convolutional neural network, is a special type of neural network that is useful in image-related tasks such as image classification, object detection, and image segmentation. It uses various filters to convolve or slide over images while extracting features from them, creating feature maps. Pooling layers are then used to reduce the size of the network while conserving important information. A typical CNN consists of a structure shown on the right with multiple convolutional layers and multiple pooling layers, followed by a fully connected layer. So in this project, the procedure I used was the following. I first collected ASL data on 100 words using the WLASL dataset. I converted these videos to frames and created datasets out of them for my training, validation, and testing datasets. And since I was using a TPU using Google Colaboratory, I needed to create distributed samplers and data loaders for each of the datasets. I then defined my 3D CNN using the i3D structure built by DeepMind and trained the model for 20 epochs. Finally, I evaluated the model on the test dataset. The image below shows the inception module of the i3D model, which is a core component of this 3D CNN used. By stacking multiple inception modules, the complexity of a network can be increased. So in my dataset, I had a total of 2,038 videos, with most of the videos being in the training set. Here's one example of a signer making the sign for book by opening and closing her hands. Here, the image shows the 100 different ASL words that were used in the study. And after training my model for about 20 epochs, the model had a mean cross-entropy loss of 2.0487 and a mean accuracy of 47.73% on the test dataset. So although the loss does not provide much information, the accuracy provides a metric on how many predictions the model got correct out of the total number of predictions that were made. So as we can see in the table below, the training had an accuracy of almost double that of the validation set, indicating that the model was overfitting. Here we can see a graph of the losses of the training and validation sets. Again, we see how the model is overfitting because the validation loss begins to plateau while the training loss continues to decrease. In this diagram, we see the validation accuracy plateaus while the training accuracy continues to increase. Again, a sign of overfitting. So although overfitting is a bad issue for model generalization, it can be solved through a couple of different ways. First is model regularization. Second is image augmentation, such as rotation, flips, and cropping as shown on the right. And third is increased data size, so that the model is always seeing new images rather than the same one. So to conclude, today, hundreds of thousands of people can communicate in only sign language, while the majority of people cannot, creating a major communication gap. Deep learning, however, has shown itself to be a useful tool on various occasions. This study illustrates how deep learning can be a promising solution for sign language translation. Although the 3D CNN model in this study did not achieve a very high accuracy, it was still able to extract important features and translate numerous ASL words to English. Still, there's more that can be done. Further study can experiment with the model structure, try to increase data size through the addition of frames, and try out different loss functions to optimize the weights of the network. Deep learning can prove to be revolutionary in the field of sign language translation, and if successful, these models could benefit millions. Thank you.